Hello everyone. Today I will present our recent paper, Generalization Performance of Hypergraph Neural Networks. This is the outline of today's talk, and I will start with the background. First, I want to introduce the concept of higher order interactions, which is almost everywhere, and it is central to our discussion. In many real-world settings, particularly on the social media, interactions are not limited to pairs of individuals. Instead, we frequently observe the group-based activities, such as the group posts, multi-participant chats, and events with multiple users. The second example is the co-author relationship. And each node in this visualization represents a researcher, and the edges represent the co-author links. So notice that the clusters are formed by the groups of authors who frequently publish together. And this indicates the multi-person connection characteristics as the higher order interactions. To capture such complex interactions, we use the hypergraphs. Here we have a visual representation of hypergraph. Unlike the standard graph, where the edges connect pairs of nodes, the hypergraphs allow a single edge to connect multiple nodes simultaneously. So on the left, you can see several hyperedges labeled from E1 to E5. And each hyperedge is a subset of the node set. And this shows how one hyperedge can can interact with multiple vertices. And in the middle diagram, each hyperedge is shown as a colored link connecting its corresponding respective nodes. And we can directly see which nodes belong to each hyperedge. Then on the right, we have the incidence matrix, where the rows represents the nodes and the columns represents the hyperedges. A 1 in a cell indicates nodes belong to a particular hyperedge, and while an empty indicates it does not. Then I want to introduce several properties of hypergraphs we use frequently in our work. The first one is M. So from the matrix, we can see each hyperedge has different size. The maximum size among all hyperedge among all the hyperedge in the hypergraph is from E2 here. So we use M to denote this size. The next notation is the maximum coordinate of the incident hyperedge sets of one node. And we use R to denote. Here we have V3, V4, and V5 have the maximum size of incident hyperedge sets, which is 2. So the last one is the neighbor. Last one is the D. So first, I want to introduce the definition of a neighbor of one vertices in the hypergraph. It consists of the nodes that share at least one common hyperedge. And we denote the degree of one node as its neighbor size. And we use D to denote the maximum degree of the nodes. Okay, this is the 3 notations. And then there are many applications and learning tasks related to the higher order relationship data. For example, search engine ranking, hyperlink prediction, community detection, and user behavior analysis. So hypergraph neural network, as one of the most successful learning models, it is a family of neural networks that are designed especially for the learning tasks on the hypergraphs. And it will model the higher order relationship through hyperedges that capture the multi-way interactions. So in the previous work, there are many popular hypergraph neural networks, and we classify them into four categories. HyperGCN, first one is HyperGCNs. It will utilize the GCN techniques to capture to the hypergraphs for the higher order interactions, and uh, it will bridge the gap between the traditional graph neural networks and the hypergraph neural network by using the hypergraph Laplacians. The second structure is a hypergraph message passing neural network. And it will directly apply the message passing mechanism, and it provide a flexible framework. For example, HyperSage, attention-based structure, model structure, and structure-based graph structure-based neural networks. And the third one is the HyperGINs. It extends the concept of graph isomorphism networks, and it always achieve a good expressive power. So the last one is the tensor-based hypergraph neural networks, and it will leverage the tensor operations that provide a structured and effective means of capturing the complexity of the interactions between higher order interactions. These models has been proved to achieve a good performance in real-world learning tasks, and some of them also have a good expressive power in theory. But in general, their generalization abilities are not clear to us. So in this work, we want to provide the very first theoretical evidence of the generalization performance for hypergraph neural networks. Uh, and we focus on the hypergraph classification task. Then I want to introduce the four representative hypergraph neural network we considered in this work, and uh, each of them uh, each of them is one of the classic models from the four categories. So the first one is UniGCN. So this UniGCN adapts the standard graph convolutional neural network architectures. And the key here is use the degree-based normalization for both nodes and hyperedges. And as shown in the equation in this slide, the UniGCN leverages the hypergraph incidence matrix to capture the higher order relationship, and then applies carefully designed normalization normalization terms to account the frequency of each node and each hyperedge appears, and the model can and we can see that the model can balance the contribution from different hyperedges during the diffusion process. The second one is all deep set, and it's inspired by the deep set framework. It introduced a powerful way to handle sets through transformations that serves as a universal approximators for multi-set functions. So in this equation, uh, we there is a node to hyperedge transformation, and there is also a hyperedge to node transformation, and each of them followed by the nonlinear activations and some learnable parameters. And this dual flow ensures that both node features and hyperedge features can be updated in a way that respects to the higher order structures of hypergraph. The third one is MIGN. It cooperates invariant and covariant transformations with a set of scalar values in each layer. So from the equation, we can see each update step scales and shifts the previous layer features based on the hyperedge connected to one node. And then it will apply the ReLU activation function. And we can see by focusing on the scalar values here, alpha, um, it will guarantee that the learned representation will respect the symmetries inherent in the hypergraph data. And this property can be particularly used in the task where the relative ordering of the nodes within the hyperedge should not affect the final representations. So the last one is TMPHN. It leverages the high-dimensional hypergraph graph descriptors, and it will explore the joint interaction among nodes within each hyperedge. So these equations, the key idea of these equations, it aggregates the messages using averaging and summation uh, uh, and the concatenation operations, and then it will apply learnable transformations to update the node and hyperpage embeddings. And this strategy ensures that both node to hyperpage and hyperpage to node interactions are fully captured, and it will and these interactions will lead to a more expressive representations of the hyperedge. Okay, now we are going to the preliminary part. So here, we outline the formal learning settings for hypergraph classification. We assume that we have a set of possible labels denoted as C, and we have an input domain that consisting of hypergraphs, each with features on nodes and hyperedges. And we also have a training set of M samples that are IID drawn from a distribution D, and each is a pair of AI and CI, the input and the labels. And we define a classifier FW, assign a real value score to each class. So to measure the performance of the classifier, we use multi-class margin loss, where the true loss is expected indicator that the correct class FWAY is no larger than the maximum of the other class scores. So formally, we have this equation, and in practice, we minimize the empirical loss, and it is the average among the summation of all the samples. So by formulating the text this way, we can systematically analyze the generalization performance of our considered four hypergraph neural network models. Okay, then the goal of learning task is that given a parameter space F of classifiers and a training set, we aim to learn a classifier FW that can minimize the multi-class margin loss, the true loss. And we use the pack-based framework to obtain the generalization bound. The prior distribution is the distribution over the parameter space, and the posterior distribution usually designed as the distribution of the learned weights based on the training data. So the standard framework provides a generalization bound for models that are random draw from the posterior distribution. And recent work focused on the margin-based generalization bound with some perturbation constraints. It usually defines Q, posterior distribution, as any fixed the learned parameter W shift by a random perturbation U that following some distribution. Then we have the following bound. The true error here is upper bounded by the empirical error plus a function of the KL divergency between the posterior Q and P, and also other parameters like the number of samples. And it is also applied, and this bound is applied to any one fixed learned parameters. So now we are ready to our main results. So from the framework, to obtain the generalization bound, we need to design appropriate prior and posterior distributions over the parameters. such that we can achieve we want to achieve three goals. The first one, we need to have a tractable KL divergence. Usually, and in this paper, we choose them both following the Gaussian distribution, and we let them share the same value of variance. And these variances are related to the value of parameters on the models. And second, we want to we want to use them to make to guarantee the perturbation constraints. So here, therefore, here we provide a perturbation analysis with parameters perturbed parameter changed over the model we consider the model FW. So and we need to use P and Q to make the following equation happens. And the final goal is to constructing accountable coverage of the hypothesis space. And the strategy here is we separate the hypothesis space into finite range. To achieving a finite coverage, it is essential to making the union bound tractable in the pack-based analysis because for because it allows for the approximation of the finite set of the possible weights within an infinite set of possible weights within a finite subset. Then we got our main results for the four models. We can see the generalization bounds of the discussed models depends on four factors. The first factor is the properties on the hypergraphs. For example, the D, R, M here. And the second factor is the hidden dimension H. And also the third factor is the number of propagation steps L, and the last one is the most important one is the spectral norm of the learned parameters. And we summarize such relationship in this table, and we can tell the differences between different models. Now we move to the experiments. So unlike previous experiments for theoretical paper, we focus on three questions. First one is, does the empirical error follow the trends given by the theoretical bounds? And second one is, how does the training influence the degree to which the empirical error consistently align with the theoretical trends? And third question is, how do the properties of hypergraphs and statistics on the hypergraph neural network influence the empirical performance? I want to first introduce the data sets. So in here, we use two groups of data set. One group is a synthetic data set. Another group is from the real world hypergraph data sets. And we compare two values, theoretical bounds and the theoretical bounds for each experiment setting and the empirical loss and the empirical errors. So the first observation is about the consistency. We can see from this figure, each subfigure plots the results of synthetic datasets and real datasets. And the figures from left to right shows the results with 2, 4, 6 propagation steps, where the value here indicates the Pearson correlation coefficients between the two sets of points in each figure, empirical loss and the theoretical bounds. And here the value is between -1 to 1, and the larger value indicates a stronger positive correlationship. And we found that the results are mostly well above 0 and even close to 1 in many cases. which indicates the theoretical bounds inform the empirical laws to a satisfactory extent with many trained models. And second observation is about the impact of training. So the figure here shows the consistent results of several data set and the UniGs and several models. And we can tell that the result review indicates an improvement in the alignment between the theoretical bounds and the empirical laws. So compared to those with compared, so we use one with the random weights, we use the one with the trained parameters. So we think one possible reason is that of this improvement is the use of L2 regularization during the training, because using this will reduce the complexity by penalizing the large weights, thereby decreasing the KL divergency. And this reduction will enhance the alignment between these two group of results. And it will give us a better generalization, better alignment between the theoretical bounds and the empirical laws. The last observation is about the impact of the data and the structures of the model. And in general, from the table, we can see the empirical results indicates clear patterns. Well, the change in the complexity of the hypergraph and the hypergraph neural networks will impact the model's parameters. And here are the conclusion and the findings. So the first conclusion is we provide a new margin-based generalization using the pack-based framework for four representative hypergraph models. And then the empirical study reviews a positive correlation between the theoretical bounds and the empirical laws. And it suggests that the bounds will effectively capture the generalization behavior of these models. And we also have several future directions. So we can apply our method. We may apply our method to hypergraph neural networks with non-homogeneous activation functions. And then we can also try some classical frameworks like VC dimensions, radiometric complexities. And we also want to further investigate the degree of the correlationship between the theoretical bounds and empirical errors. This is all of today's presentation.